we have talked and will continue to talk at length about how to make good images, what to do with the camera, what to do with the lighting, what to do with your composition to make the image look good. But equally important to that is making the image sound good. Well, making the soundtrack sound good. Audiences will forgive bad images if the audio is good. And there are reality shows that attest to this. Cops was a good example of this. Horrible video, but the audio was always clean, and it did really, really well during its run on television. The converse is not true. Audiences will not accept good images if there's crappy audio. They just won't stay focused. They won't stay with the program. So we need to spend a little bit of time on audio. So this particular lecture, we're going to talk about the nature of sound. This is going to set you up with some theories and some concepts, and then we will move into specifics about how to apply these concepts to what it is we do, making moving pictures. So here's a video that I borrowed from YouTube that very shortly, very concisely sums up the idea of what sound is.
When an object vibrates, it pushes the surrounding air molecules into one another, starting a chain reaction of collisions through the air. These collisions travel in waves. When they strike your eardrum, it vibrates. This vibration is converted into electrical signals that your brain recognizes as sound.
So when it's undisturbed, air is just sitting there. All of the molecules of air are more or less evenly distributed in the room, outside, wherever it is you happen to be. But as soon as a vibration changes that, you get these expanding waves of energy. And like you saw in the video, they're alternating waves. There's a high-pressure wave followed by a low-pressure wave. So in that high-pressure wave, the air is actually compressed together, and we call that compression. The low-pressure wave, there's actually a little bit of a vacuum left where the molecules came from, and we call that rarefaction. So what sound is an alternating series of compression waves and rarefaction waves radiating outwards over space. Forgive my primitive animation here. If we look at it on a graph, you can see that as time progresses, it's cyclic. It alternates between being higher than normal pressure and lower than normal pressure, higher than normal pressure, lower than normal pressure. And if we look at one repetition of that, one cycle of that, right, it starts with the air pressure being normal, the air pressure increases, decreases back to normal, continues to decrease to below normal, and then comes back up to normal. So that is one cycle of sound waves. We measure how often those cycles happen in 1 second. And we call that measurement the frequency. How frequent are these sound waves? During 1 second, how many sound waves reach our ears? We measure this frequency, or we perceive changes in frequency as changes in pitch. The lower the frequency, the lower the number of sound waves reaching our ear in 1 second, the lower we hear the pitch of the sound. As that frequency accelerates, as it gets faster and faster, as more and more sound waves impact our ear in that 1 second window, we perceive that as getting to be a higher pitch, right? So it's the difference between a bass guitar and a piccolo. Simply the number of sound waves per second that are reaching our ear. The other thing we need to pay attention to is how strong those sound waves are, how much air is physically being moved. And we measure that with a measurement called amplitude. Amplitude we perceive as volume. So the larger the amplitude, the physically more air is being displaced by these sound waves, the louder we perceive that sound to be. The frequency, or what we hear as the pitch, again, is measured in cycles per second, and we call this measurement hertz. This is named after a radio engineer, so because it's a proper name, the abbreviation HZ always has a capital H. Human ears, at their best, can hear from a low of 20 hertz to a high of 20,000 hertz, or you might prefer to say 20 kilohertz. Most of you are coming up, you're in your early 20s or maybe the very end of your teens. You've already begun to lose some of that high-end hearing. You can probably hear up to about 18 kilohertz by now. I used to be a headbanger. I really liked my music loud. I'm also in my 50s now. I peak at about 15 kilohertz. Beyond that, I really can't hear anything. And this is just natural. Hearing loss comes in part from age and in part from living in an industrial society where we have things like headphones and iPods. Our most sensitive range is between 1 and 4 kilohertz, and this is also coincidentally where most of our vocal range falls, that range between 1,000 hertz and 4,000 hertz. Here are some examples of what a frequency sounds like. 41 hertz, this is the lowest E on a 4-string bass. "60 hertz is the most annoying sound in America. This is the hum that gets introduced into your sound feed by unshielded electronics. "440 hertz, if you've ever tried to tune a guitar using a tuning fork, this is the sound that you started with. "High C on a piano. This is the highest note on a typical 88-key piano. "8 kilohertz. This is just a high-pitched whine. We could go higher and test the limits of your hearing, but you get the idea. There's a correlation between the faster those sound waves arrive at your ear and what you perceive as the pitch of that sound. The amplitude, or the volume, we measure in decibels. Decibels are named in honor of Alexander Graham Bell, one of the inventors of the telephone, is probably where you know the name from. He had a unit of measurement that he called the bell. But a bell by itself is actually too clumsy to work with. It's too big a chunk of measurement. But if you cut it into 10 pieces, it becomes very useful. 1/10 of a bell, or 1 decibel, is a very convenient unit of measurement. Again, because it's named after a person, the B is always capitalized. So small d, capital B for decibel. Decibels and hearing perceived loudness are weird. It doesn't work the way you think it would. If you double or half the amount of sound energy that's reaching you, you're changing things by 3 decibels. We're obsessed with doubling and halving, all right? Every time we're talking about exposure, when you change a stop, you're either doubling or halving the amount of light that's coming in. We're also obsessed with doubling and halving when it comes to sound, but it doesn't work quite the same way. So again, if I'm in a room and I have 2 televisions playing with equal volume, and I turn one television off, the room overall gets 3 decibels quieter. However, if I'm on an airplane and there are 50 screaming children on that airplane, but half of those children go to sleep, it still only gets 3 decibels quieter. Every time you double or half the amount of sound energy, you're changing that overall amplitude by 3 decibels. Your ears work, hearing works on a logarithmic scale. And the logarithm of 2 is 3, which is why it's 3 decibels. Okay, you don't need to remember logarithms. It was a dirty word when you had it in high school. There's no reason to dredge it up now. But just understand that the way your ears process sound is very different from the way your eyes process light. So even though it seems like 25 screaming children ought to be a more profound difference, it's really only 3 decibels quieter than 50 screaming children. Here's a few examples of what loudness is like. Somewhere in the area of 70 decibels is where people tend to start agreeing that things are loud. As you get louder than 80 decibels, you're into the range that with enough exposure, you are going to cause hearing damage. I'm going to talk a little bit about audio phase now. Audio phase is an interesting concept, and this has to do with what happens when you combine 2 or more signals that are taken from the same sound. So in the example here, you can see that we have a person sitting at a desk with 1 microphone. And there at the top, you can see the graph of the sound wave as he's talking or she's talking. Nothing complicated about this. When we add a second microphone, and we put the second microphone at the same place as the first one, it's the same distance away. So it's recording the same sound, and it's the same distance from the speaker. So if you look at both of those graphs, if you look at both of those audio waveforms, they're the same, right? The high points line up with each other, the low points line up with each other. The sound waves are reaching the 2 microphones at the same time, so they're perfectly synchronized. We call this being in phase. And if you take two audio signals that are in phase and you combine them, you simply get a louder audio signal. That makes perfect sense, doesn't it? All right, let's go back to the start of that example. Here again, we have our person at a desk with one microphone, and we have the one audio waveform that we're looking at. This time, when we add a second microphone, it's farther away. So the person standing there with the boom mic is a few feet farther away from the speaker than the original microphone was. And he's recording the same sound, but because he's physically farther away, there's a very slight delay as the sound waves travel outwards. It takes longer for them to get to the shotgun microphone than it does to get to that desktop microphone. So if you look at this, you will see that they are no longer synchronized. In fact, they are completely out of sync. When you have a peak on one signal, you have a valley on the other. This is referred to as being out of phase, and these guys are 180 degrees out of phase. They are perfectly, completely out of phase with each other. Well, what happens if you combine two audio signals that are identical but are out of phase with each other? You get nothing. This is called phase cancellation. Phase cancellation is a real issue sometimes. If you want to try and do this as an experiment, it is almost impossible to place two microphones at the exact distance so that they will completely cancel out your voice and record nothing. But it is very easy to have two microphones set up such that if they're both turned on, the volume of your voice dips. I see this often in our studio class. When we have 3 or 4 people on set, everybody has a microphone attached to them. When you bring up the first microphone for the host, it sounds beautiful. And the host introduces the show. Hi, I'm Tom. Welcome to my show. Let me introduce my guests. So you turn up the other 3 microphones for the guests, and all of a sudden, the volume of the host's microphone drops, and it drops a lot. Suddenly, you can't hear what they're saying anymore. This is phase cancellation at work. One of those other microphones that you've just turned on is at a distance such that it is picking up the same sound but out of phase, and those are getting combined in a mixer, and they're eliminating each other, or they're fighting each other, reducing the volume. So if you're working with multiple microphones, by multiple, I mean more than one, if you're working with 2 or more microphones on a single talent, phase cancellation might become a problem. You need to be aware of this as you're editing. Now let's talk about mic placement. As sound travels, it gets weaker. There's no big surprise here, if you forgive my clumsy animation there on the screen. It gets weaker according to something called the inverse square law. Okay, this goes back to high school geometry again. We're talking about the surface area of a sphere. So as I talk, the sound from my voice is expanding in all directions more or less equally. So it's expanding as a sphere. If you remember the formula for a surface area of a sphere, it's 4 pi r squared. Okay. High school geometry has come back to haunt you. So if we imagine in this example, we have a bird singing and we have placed 4 microphones at various distances. And it doesn't matter what that distance is. That distance could be feet, it could be yards, it could be kilometers, it could be football fields, it could be bananas, as long as we're measuring a consistent distance. Let's pretend that this is yards. Okay, so we're going to have a microphone at 1 yard, 2 yards, 3 yards, and 4 yards from that bird. So at a distance of 1 yard, the sound energy coming from the bird has to cover a sphere that's about 12 square yards, and that's where our first microphone is. By the time it gets 2 yards out, it has to cover a sphere that's 50 square yards. That's 4 times as much area. By the time it makes it 3 yards, that same energy is spread out over a sphere that's 113 square yards. That's 9 times more surface area than it was at 1 yard. And by the time we get to 4 yards from the bird, that same energy is spread thin over a sphere that's over 200 square yards. That's 1/16 as much energy in a spot as there was 1 yard away. So remembering that every half is a change of 3 decibels, right? If we cut the sound in half, it's 3 decibels quieter. We cut it in half again, that's a total of 6 decibels quieter. If you look at these, so at 1 yard, this is our basic measurement. We are not losing anything yet because this is where we started measuring. So we've lost 0 decibels of sound. By the time we get out to 2 yards, we've lost 6 decibels of sound. It's 1/4 as strong as it was. By the time we get out to 3 yards, it's lost 9 decibels of sound. It's 1/9 as strong as it was. And by the time we get out to 4 yards, we've lost 12 decibels of sound. It's 1/16 as strong as it was. So you can see that the sound falls off very quickly as the distance changes. A small change in distance is a large reduction in the amount of sound energy reaching the microphone. Knowing the math is sometimes helpful, but if the only thing you can remember from this is the following, then remember the following. Closer is better. When you're placing a microphone, closer is better. Right now I have a microphone that's maybe 18 inches from my mouth. It's barely out of frame right there. Closer is always better. Part of the reason why is because of that change in volume, but that's only half of it. The other half is something called signal-to-noise ratio. Now, when we set up to record our bird, or when I set up to record myself, there's other sounds that are going to get recorded. This is just the reality of life. In the room that I'm in, there are cooling fans attached to equipment. There's air conditioning blowing. There's even occasionally people walking by outside. I can't stop those noises from reaching the microphone, but what I can try to control is making my voice so much louder than those other noises that you don't really notice them. Okay, so my voice is the signal, and all of those other sounds are the noise. So what I want is a very strong signal-to-noise ratio. I want a lot of signal to a little noise. The same thing with my bird. The bird song is the signal, but I'm recording the bird outside. So things I might have to contend with could be the sound of the wind. It could be distant traffic. It could be people playing in the park. All of those other things are noise. The bird song is the signal. So if we look at this at a graph level, if I have the microphone at a distance of 1 yard from the bird, right, and I've got no drop off. This is my first microphone, so there's a 0 dB loss. So according to my chart, the bird is singing at 80 decibels. That's one loud bird. And the background noise is about 30 decibels. Okay, so there's a pretty good spread between the signal and the noise. If you look at that same graph, by the time I have moved my microphone back to a distance of 4 yards, I've lost 12 decibels. So that makes it, 68 decibels of bird song, but I've still got that same 30 decibels of noise. My signal is now only twice as loud as my noise. Before it was closer to 3 times as loud. We can fix the volume, right? I can take that recording from the second microphone and I can make it louder in my editing software. But when I make it louder, I'm also going to make the noise louder. So let's see what that looks like on a graph. So again, if you look at that first column, you can see that that's my original recording where I had 80 decibels of bird noise and only 30 decibels of background noise. The middle one we saw earlier, this is what the recording looked like at 4 yards away. But that right-hand column, I have now taken that recording from the 4-yard microphone and I have forced it to be louder. I've used my editing software and turned up the volume on it. I've got my 80 decibels of birdsong back, but now instead of having 30 decibels of background noise, I've got 42 decibels of background noise. Because when I turned up the volume on that recording, it turned up the volume for everything, not just the birdsong, but the noise. So my signal-to-noise ratio is not as good. So even though I can get the volume from that farther microphone by enhancing it electronically, I can't get as good a recording because there's more noise in the background. There's more noise competing with the birdsong. Okay, looking at an example of a bird with some lines drawn and some imaginary microphones is one thing. Let's try this in person. I'm going to set up a shot where I'm going to have this microphone and I'm going to measure off some distance on the floor. And I will stand at 1 yard, 2 yards, 3 yards, and 4 yards from the microphone. And I will talk to it. I will say the same thing from each distance. And we will put this together so you can hear not only the drop off in volume as I get farther and farther away, but also I'll crank up the volume so that you can hear the change in the signal-to-noise ratio between the two. Hi there, I'm Tom. I'm standing 3 feet away from the condenser microphone. If I had to guess, you're hearing my voice very strongly, but there's a lot of air conditioning in this room. There's a lot of ambient noise I normally filter out you're probably hearing right now. Hi there, I'm Tom, and I'm now 6 feet away from the microphone. Hi there, I'm Tom, and I'm 9 feet away from the microphone. Hi there, I'm Tom, and I'm 12 feet away from this microphone. We the people, in order to form a more perfect union, establish justice, ensure domestic tranquility, provide for the common defense, promote the general welfare, and ensure the blessings of liberty to ourselves and our posterity, to ordain and establish this Constitution for the United States of America. There are a lot of takeaways from this. The principles of audio are important to understand and important to remember as you go forward and start working with various configurations of microphones and other sound sources. Be sure to take away how sound is measured, both frequency in terms of hertz and amplitude in terms of decibels. The human ear at its very best can hear from a low of 20 hertz to a high of 20 kilohertz. Again, most of you have already lost some high-end hearing. This is just the cost of growing up in a first world nation. Lots of noise pollution, lots of opportunities to damage hearing. Some of us who are former headbangers have damaged our hearing more than others, but, well, I had a good time. I had fun at the time. Remember when we're talking about amplitude, that every change in 3 decibels is either doubling or halving the amount of sound energy that's reaching the microphone or reaching your ear. Remember the idea of audio phase. If the audio signals are going up and down at the same time, if they're coinciding that way, they're in phase. If they're not going up and down at the same time, they're going out of phase. And if you get them to the point where they're actually opposite of each other, where a peak on one is a trough on the other, then they're 180 degrees out of phase. They're completely out of phase. If you ever get a chance to do an experiment with this, and if you listen to a microphone or signal as the microphones start in phase, and then you slowly move one of them away as they start to drift out of phase and get further and further out of phase, it's really entertaining to listen to the change in the audio signal. We might try to do that at some later point. It's very difficult to do it well. What the hell? I'll commit to it. We'll give it a shot and see if we can't make it happen later in the semester. The inverse square law is important, and it applies not just to audio, but to lighting, to anything that expands on a spherical wavefront, heat, gamma radiation, sound, light, anything like that. You don't necessarily have to remember how to do the math on that, but remember the following. Closer is better. And this is really especially true when you're working with microphones. Closer is better, and small distance changes make large audio quality changes. Right. So I've got this microphone just as close as I can get it without having it in the shot. I actually would prefer to have a lavalier on, but there are other complications working with that. So this is much easier for me. And remember the idea of signal to noise ratio. What we're going for ideally is no noise, but that's just unrealistic. You're going to have noise anytime you have a microphone in action. So you want to have the best signal to noise ratio you can. You want as much signal with as little noise as you can possibly get away with.